So this activity is talking about indirect measurement. We use indirect measurement when we're trying to find the length of something that isn't easy to measure with tools like rulers or tape measures. For example, maybe you want to know how tall a tree is. Well, you wouldn't want to measure that with a tape measure. Or maybe you want to measure the distance across the galaxy from one planet to another. Again, not something you can measure with a ruler. So when you're measuring really big things like that, or sometimes even really small things, we use indirect measurement to do that. And some practical tools that you might use every day for indirect measurement are shadows, reflections like from a mirror, and transversals. Those are three basic types of problems you're likely to see. So let's take a look at those three problems here. So shadow problems, how do those work? Well, in this problem we have a girl, her name is Daniela, and we have a tree. We know how tall Daniela is, and we want to know how tall the tree is. Let's see what the problem tells us. It says Daniela is 5 feet 4 inches tall, and her shadow is 2 foot 1. We don't know the height of the tree, but we do know that the shadow of the tree is 4 foot 2 inches long. What else do we know? Well, we know that both Daniela and the tree are standing at right angles with the ground. So there's 90-degree angles there. So when we look at the triangles that have been drawn here, we know that they have at least one pair of congruent angles. What else do we know about these triangles? Well, the hypotenuses of these triangles both represent rays of sunshine. And we say that rays of sunshine are all parallel. So since these sun rays are parallel, we can say that our top angles here are also congruent. So CAB is congruent to FDE. So we know that these two triangles have two pairs of congruent angles, which means that triangle CAB is going to be similar to triangle FDE by angle-angle similarity. And you can use that with anything that has a shadow. You can always draw two similar triangles like this with objects that are casting shadows. So now that we know that, let's go ahead and solve this problem. The first thing I'm going to do is change all these feet and inches to inches. We need a common measure of unit. So 5 foot 4 inches would be 5 times 12 plus 4 inches. So 5 times 12 is 60. 60 plus 4 is 64 inches. And then we'll do the same process with the other two. Great, so now we've changed all of our measurements from feet and inches to just inches. So now let's write a proportion comparing the heights and the shadows of these objects. So I've written this proportion here, and this one's actually pretty easy to solve. It's because I know 25 times 2 is 50. That means I can just multiply 64 times 2 to find the height of my tree. So now I can tell that my tree is 128 inches tall, because 64 times 2 is 128. Maybe I want to know that in feet. If I wanted to know that, I would do 128 divided by 12. So when I divide by 12, I find that 128 inches is the same thing as 10 and 2/3 feet. Well, what is 2/3 of a foot? Well, here's a foot. It's 12 inches. And here's what that foot looks like if I split it up into thirds. So what would 2/3 be? Well, let me shade 2 of these thirds. There we go. And you can tell now that that's the same thing as 8 inches. So 128 inches is the same thing as 10 foot 8. So those two answers mean the exact same thing. You can use whichever one you want. So that's a shadow problem. All we did was use similar triangles that have two congruent pairs of angles to write a proportion comparing the length of the shadows to the heights of the objects. And since the sunshine has parallel sun rays, you can do this with any object that casts a shadow. Just write a proportion comparing the heights and the lengths of the shadows. Another type of problem you're likely to run into is a reflection problem. For this one, you can create similar triangles by putting a mirror on the ground. What you do is you put a mirror on the ground and you walk backwards until you see the top of the object that you want to measure in the mirror. So that's what this problem says is happening. Julio uses a mirror to estimate the height of his house. Julio places the mirror on the ground and walks backwards until he sees the top of the house in the mirror. So what that means is there is a mirror right here at point E. And Julio walks backwards until he can see the top of the house in the mirror. Now Julio's eyes are 60 inches above the ground. and he is 20 inches away from the mirror. The house is 8 feet away from the mirror. We want to know the height of the house. So with a reflection problem like this, you're going to compare the distance from the mirror to the height of the object. So Julio is 20 inches from the mirror, and his height is 60 inches, or that's the height to his eyes right here, because we want to measure up to your eyesight, your eye line. The house is 8 feet from the mirror, and we don't know its height. So there's our proportion. This is another simple one to solve because 20 times 3 is 60. That means I want to multiply 8 times 3, and that's going to tell me that the height of this house is 24 feet. And that was calculated without rulers or tape measures or anything, just measuring the distance from a mirror. So there's one more type of problem you're likely to run into, and this one uses parallel lines and transversals. So here in this case we have Myron measuring the distance across a forested area of the city park. He knows that he needs to find the length of AD. So he's looking for this right here. So he draws two triangles, triangle AED and triangle CEB. And he draws them so that AD is parallel to CB. So since those two lines are parallel, we have parallel lines cut by a transversal here. So Myron does some measuring and he finds some of the lengths of the triangles. He finds that DE is 25 yards and EB is 40 yards and then BC is 65 yards. So really quickly, let's just think about what else we know about these triangles. Well, first of all, we know that they have congruent vertical angles right here. So there's a pair of congruent angles there. Also, AC and DB are transversals of our two parallel lines. So we know that angle DAE is going to be congruent to angle BCE. Those are alternate interior angles formed by parallel lines. And the same thing is also true for angles ADE and angles CBE. So we know that triangle ADE is similar to triangle CBE. So I used my highlighters to identify my corresponding sides of these similar triangles, and then based on that, I wrote a proportion here comparing the side lengths of my triangles. Now I just need to substitute the lengths of my triangles into this proportion. So I'm going to use my cross products now to write an equation. If you want to use smaller numbers, you could simplify your proportion a little bit first. I divided both of my numerators by 5 to simplify it to this. And whichever equation you use, you're going to get the same result, that x is equal to 40 and 625 thousandths of a yard. So that's the distance across our little forested area. And again, all we did was use similar triangles. We identified those because we recognized the lines were transversals cutting parallel lines. And then we used that to compare corresponding sides of similar triangles and write a proportion. This is a great strategy for measuring distances across things like rivers and lakes and swamps and any area that would be difficult to measure on land. So in summary, we looked at 3 different strategies for indirect measurement: using shadows, using reflections, and using intersecting lines. And all 3 of these strategies allow us to use similar triangles to write proportions to find the distance that we're having difficulty measuring.